All right. Hey. All right, everybody. I was just checking Jake out. Jake got tired of me. Maggie's laying over there. And I hope you have a cup of coffee. And I hope you have your copy of NFPA link open. Because I do. And I just made that cup. And it is, I could stand a spoon in there, David. So we're going to dig into Article 430, and we're going to dig into conductor selection, overcurrent protection, same topic. Again, we're talking ampacity of conductors, ampacity of conductors, ampere rating of overcurrent protective devices, and we talked about Article 210, 215. We also talked about Article 230 and some of the special provisions that are in 310. I believe it's 310.14. If my memory serves me correct, I could be wrong. But we have Don Gannier and Eric Hecker, and we've got John McCamish, and we've got Steve on the phone who will check me, and David Engelhardt. So what I'm planning to do is I know John McCamish said, boy, you got some guts going live and you have no idea what the heck you're going to talk about. Well, at least I have a topic I'm going to talk about, and I did not prepare anything. So, and that's a good thing because we're going to walk through the process. Hey, Felix Sandoval, I'm drinking some Colombian roast. So, salute, Felix, salute. And look, I don't know if you can get this. Can you get it? A house is not a home without pause. So, okay. So let's do this. Before we even look at the code, let's talk about, hey, I got that right. Let's talk about the basic layout of a motor circuit. We know we're going to have, I don't know if it's a motor control center, it could be a panel board, it could be a switchboard, it could be any place where I am going to install what? A circuit breaker, right? So, or overcurrent, I'm going to draw it as a square, and I'm going to call this an OCPD. Overcurrent protective device, because it could be a fuse or a circuit breaker. I apologize for the notification bleeps, but I'm going to leave those in because I need to know when someone is making a comment, and I think my wife might be home. So, anyway, I'm going to come down to what let's think about a motor circuit. Let's do that. I'm going to draw the motor. I got to draw the motor. All right, so there's our motor. We come off of a circuit breaker, and we're going to come to what? Probably a piece of equipment. So I'm going to draw a box to represent a piece of equipment. And what is going to be in this equipment? I'm going to have a contact and a overload. And then I'm going to come back down to probably, now maybe not, or maybe not, a piece of equipment. And I'm just going to say it is a piece of equipment, and I'm going to hit a motor, right? So this is going to be a dupe. This is my disconnect. And I put the contactor and the overload in the same box. I'm going to call this my controller. So I'm going to say, I'm just going to have contactor and overload. Right, so I have my overcurrent. Now also, I'm going to have a conductor here. I'm probably going to have a conductor here. Tell me where I might be going wrong. I am just flying by the seat of my pants. I'm going to have a conductor there. All right? So I have my overcurrent protective device at the source of my branch circuit. Off of that, I'm going to have a conductor. It's going to go to my motor starter, I'm going to call it, but it's a contactor and an overload. And then I have another conductor to connect my disconnect, because my disconnect's required under specific rules of the NEC. And then I go to my motor, and I'm going to have another conductor going to the motor itself. Make sense? Perfect. Okay, so that's basically the circuit. Now, what do I know? I know that I got to provide protection. I got to protect the motor. Protect the motor. I got to protect the motor from overload and short circuit. I also have to protect, I'll call it the contactor / overload equipment. That's going to be your starter, I guess you would call it, from overload and short circuit. I have the conductors. All of my conductors I have to protect from overload and short circuit. You know what? Ground faults are in there too. I want to throw ground faults in there too. And basically it's overcurrent. You know what I'm going to do? Here's what I'm going to do. This is better. Overcurrent protection. Why do I say overcurrent protection? Because Dawn, you're right. It's or a motor circuit protector in a combination starter. Yeah, so that's the other issue is there's a lot of different variations, right? My overcurrent protective device could be a motor circuit protector. It could be a standard overcurrent protective device. I could have a lot of different scenarios. So I'm just saying I've got an overcurrent protective device, which a motor circuit. It's a good discussion, actually. Good point, Dawn. A motor circuit protector is not an overcurrent protective device. So why do I say that? Let's draw the time current characteristic curve for both. Remember, a time current characteristic curve. Soft starter could be that's right, we could have a variable frequency drive in there too. So across the bottom we have current, and up the side we have time, right? So if I think about your standard overcurrent protective device, I'm going to have something that looks like this. All right, so this is your overload protection. And this is your short circuit protection. This is an OCPD. What a motor circuit protector is, I'm going to draw it side by side. And I'm going to draw the motor circuit protector in red. A motor circuit protector looks something like this. All right, there's no overload protection. So this is an OCPD that has overload protection and short circuit protection. This is, I call it just a motor circuit protector, instantaneous only trip circuit breaker, whatever you want to call it. I think the code calls it an instantaneous trip circuit breaker. I think an industry term is motor circuit protector. And what the intent is that the overload, I'm going to draw it in green. No, I'm going to draw it in green. No, I'm not going to draw it in green. I'm going to draw it in purple. This is your overload protection. And that purple curve would be right there, okay? So this could be your motor circuit protection, and this is your overload. So between the motor circuit protective device, that red curve, and the overload curve, combined together, they provide protection of the circuit for you, okay? So what I think, this is what I'm hoping, my thought process is, did you have fun? Good. My thought process is that, remember our goals over here. We have to protect the motor. We have to protect those contactors and the overloads, or the controller. And to Felix's point, Felix made a point. It could be a soft starter. It could be a variable frequency drive. We'll get into all those little details, and this is going to be a multiple series type of event. But every component has to be protected, right? I can't have a circuit that does not provide protection. It's not like that God came down and said, you do not need to protect this circuit. You need to protect the circuit. We're going to hopefully in this journey show how every component in this circuit is protected, and I want to understand why. And we're going to do that in combination with the code, but I want to make sure that we go about it not looking at the code first, but I just want to go about this discussion as understanding the circuit, and we will confirm with the code. Make sense? Okay. So that's I think the journey that I want to take. I don't want to go to the code and try to understand Article 430 and how it's laid out. I want to understand this circuit, and then we'll change different components. But this, I think, is your standard basic motor circuit. You've got your overcurrent device, you've got a conductor coming off of the circuit breaker, whether it be a motor circuit protector or a circuit breaker, and we'll go through that process. Then you're going to feed and what I've seen is, I've seen I think Allen Bradley, Cutler Hammer, Westinghouse, Eaton, Schneider, etc. I remember purchasing and installing a motor starter. Basically, it was a contactor and the overloads. And the Allen Bradley, the Rockwell ones, they were the little round white. They looked like little donuts. You put them in, and they had little ears on them. You'd put them in, screw them in. The Cutler Hammer ones that I remember on the Freedom Series starters, they had a flat, and when you took the overload out, it was like a little worm that was in there. The current was going through, and those units, when I worked at Crystal River Unit 3, I learned that there's a voltage drop across those because it's a resistance value. And when I was working at Crystal River Unit 3, which was a nuclear plant, I wrote a program that basically did the voltage drop studies for single phase used in emergency systems. So to validate we validated the software, okay? We did hand calculations. So we had a separate person doing hand calculations. I was writing software to implement the hand calculations, etc. We would compare answers, all that jazz. But then when we went to the Nuclear Regulatory Commission, I remember sitting in the meeting, and somebody asked the question about the elevated temperature in certain areas of the plant, and do those overloads have a resistance value? And of course they do have a resistance value. And they do change based upon the ambient temperatures and things like that. So I had to do a lot of testing to understand the impact of the thermal impact on an overload. There is a resistance there, and when you're off of like a battery load profile type of deal, and you're running on limited battery energy, and you only have so many hours to get the plant shut down, there's some challenges there. So, but in any case, those overloads are oftentimes built into the starters. All right, Steve says, oh, Don Gannier says first, there are no overload protection on the line side of the starter. Well, I have an overcurrent protected device. There is we're going to get into overload protection. I know where you're going, Dawn, and you're right. The overcurrent protected device upstream is not there for overload protection. That's why you have overload protection for the entire circuit. It's there. Where it's at doesn't matter. I don't care where you put it because overload protection assumes all of the current is staying in the path. The short circuit protection assumes current's going outside of the path, so it's very critical on where you put your short circuit protection. So I get where you're going, and we'll get there. Thank you. Steve, and remember to watch the AIR and or SCCR of everything, ampere interrupting rating, that's your interrupting ratings, and your short circuit current ratings of everything is in the overall. That's right, and that's why I said over here, I said, and I'm just going to do this overcurrent protection. I'm going to write it overcurrent protection. Overcurrent protection. Overcurrent protection. I can't get out of not providing overcurrent protection. I have to. I mean, it's a fundamental rule from a safety perspective. I can't have a conductor, a piece of equipment that doesn't have protection. And when I put overcurrent protection, that means I'm protecting things from ground faults, short circuits, and overloads. Go back to the definition that is in the code for overloads, and overcurrent. I'm sorry, overcurrent. All right, so I got to protect the motor. I got to protect the components, the disconnect switch too, right? Contactor, overload, and I'll throw the disconnect in there too. The disconnect is going to have a short circuit current rating to Steve's point, and I have to make sure that all of those components. That's why in many motor starter or motor control centers and whatnot, they'll look at all the different components to make sure that whatever is the short circuit current rating that I need for that system, I get, and that will be looking at the contactors, the starter, if there's any power distribution blocks or whatever that might be in the controller configuration. All of those components are going to be looked at to find out the weakest link, and then that's your overall short circuit current rating. So all of this equipment is going to have a review for short circuit currents. All right. So that's our goal. I mean, I can change out to our point, the starter, to Felix's point. I can say, hey, you got to put in a soft start or a variable frequency drive, all these different things. But regardless, this is our basic circuit. Now, what I know based on this circuit, let's do this. I'm going to copy this. Copy. I'm going to scroll down. Paste. I'll paste that puppy right there. All right, so let's get rid of that for now. Let's talk about the conductors. Geez, conductor. So, because we're talking ampacity, and we're talking ampacity, and we're talking overcurrent protection. So I'm just going to start with the conductor itself. What are some of the things we know? The conductor is going to have an ampacity. Oh man. The conductor is going to have an ampacity based upon the conditions of use. So it's only going to be able to carry so much current. Now, what current does it have to carry? Well, the motor current, right? The full load amps of that motor, the full load amps of the motor. I don't care if it's a continuous duty motor. I don't care if it is going to operate continuous. It's only going to operate like my pump does downstairs, only every so often when the water fills up a little bit. On the HVAC system, I have a pump down there on a dehumidifier. Puts the water in there, and there's a little motor in there that every now and then turns on. You might have a fan, a very large fan. It could be an induced draft fan on a power plant. It could be on a conveyor belt, and that conveyor belt could be running all day. I don't care. I just know that it needs to carry the full load amps continuously, period, based upon its ampacity. Hey, Redondo. Greetings. Good afternoon from Costa Rica. Hopefully Costa Rica is good. Yes. Oh, excellent. You teach this class, so perfect. Redondo, if you have anything to contribute, anything to add, if you see where I might be going astray, that's what this journey is all about. So thank you for joining in. We are truly an international program as of Felix Sandoval in Colombia and Redondo in Costa Rica. And I don't know where, I can't remember where Nihad is. Nihad, I think, is over in Egypt. I don't know. Anyway, or Indonesia. I don't know where he's somewhere. So anyway, so that's our journey. So we know that conductor has to carry the amps of that motor. And we know that the conductor is going to carry the locked rotor amps for a short time. Right? It's no different than, I would liken a motor to a transformer. When I think about a motor, if somebody would say, how would you treat the motor? I would treat it very similar to a transformer when I'm thinking about the impedance and the model, the impedance diagram of a motor. Think about it. On a transformer, I have a core, an iron core. I have windings, and I will have flux, and I will generate currents between one winding and another, essentially through an iron core. A motor is very similar, and if you looked at the diagram, and maybe in one of these sessions, I'll grab the model, the impedance model for a motor and the impedance model for a transformer, you will see they are very similar. So I would say that just like in a transformer, the conductor that feeds a transformer is going to have to be able to exist during inrush currents, but I would not expect an inrush current on a transformer nor the inrush current in a motor to persist long enough to damage the conductor. That's why you need your overcurrent protective devices to take that motor or the transformer offline should an inrush current or an overcurrent, so to speak, persist too long. All right? So I know my conductor is going to have an ampacity, which is based upon the conditions of use. Yes, he is from Egypt. He lives in Saskatoon, and he travels a lot. So I think he is. I don't know if he was in Indonesia. I'd have to look at where my last communication was with him. But he is all over the place, David. You never know what part of the globe that guy is going to be in. All right, so we have a conductor, we have an ampacity, we have what current does it need to carry? It needs to carry the full load amps, at least the full load amps. So the ampacity, somewhere in the code, we're going to have requirements that say the ampacity of this conductor has to be able to handle that full load amps. And we have to have the locked rotor amps. Now, the thing about a motor, depending upon what it's on, my full load, let's talk about the motor start curve. Let's talk about the motor start curve. if I go back to my time current characteristic curve, I have amps along the bottom. I have time along the side. Now, motors, when you first start them up, they're going to have a locked rotor amps. So typically on a motor, I'll have, say, a current, say this is my locked rotor amps. Now, when you first start a motor, that first cycle, maybe a little less than a cycle, is asymmetrical. So typically on a motor start curve, we'll draw, I call it a foot. And it's usually below the 0.01 second line, and it's like that. That's called, I call it the foot. And that might be critical depending upon your overcurrent protective device upstream. You may wonder, why am I tripping my circuit breaker? And it could be because of that asymmetrical. When I say asymmetrical, this is symmetrical, this is asymmetrical. That is that first half cycle or so, RMS-wise, it's going to be a little bit higher. So we'll draw on a motor starting curve a foot. All right, so then we have the locked rotor amps, and then we know what the full load amps are up here, okay? The full load amps are going to be less than the locked rotor amps. We know that. So we know that at some point we have to transition from locked rotor amps to full load amps, okay? Oh, Mr. McCamish is leaving. Sorry, buddy. We can always watch it later, bud. Carl Lewis says, I live. Okay, Carl. I'm glad you're here. We're all glad you're here. So at some point, we have to transition from a locked rotor amps to a full load amps. So we know for a period of time, all motors are going to, Robert from Omaha, good to see you, buddy. Thank you, and thanks for joining in, and I hope you are feeling well. So at some point, I'm going to transition from locked rotor amps to full load amps, and that transition point, I am going to just do this, and I'm going to do this, and I'm going to do that. That transition point is going to vary based upon the motor and the load, right? So I know my motor load is going to be pulling current that is going to vary based upon what it is I'm driving. If I'm driving a conveyor belt and it's a loaded conveyor belt, for example, my transition point might take a longer period of time. So maybe my transition point on a conveyor belt takes longer time to get it up to speed because I'm working hard, and then once I get that belt up to speed, I come down to full load amps. And maybe I don't even get down to full load amps because I'm still working hard and I'm going back and forth. This could be a fan where, let's do that. Let's do a fan. Let's do a fan, right? I might do this on a fan. And that transition point between locked rotor amps and full load amps on a fan, because there's very little resistance, can be very quick. You turn it on and it's at full load amps. And you're just doing the locked rotor amps to get that rotor turning and the fan turning. So it depends upon the weights of the blade. What is that fan? Is it just pushing air? The fan, is it trying to drive water? Is it like a pump? What's going on with the fan? So anyway, we know the conductor is going to have to carry this current, and the code is going to have rules to tell me how to size my conductor. All right? Okay, so from a conductor perspective, I have ampacity. I know I have to carry the full load amps of the motor. I know that I'm going to have locked rotor amps in there for a short time. And I'm going to put a question mark there because I know that how often I'm going to be required to pull locked rotor amps is going to be dependent upon what it is that I'm driving. If I'm driving a conveyor belt, I may be in locked rotor amps depending upon the starts and stops, all that jazz. All right, so that's sort of the picture for the conductor. When it comes to, I am going to copy. Well, let's continue on. Let's talk about the motor. Let's talk about the motor, because I need to know, why can't I write? All right. I need to know for the motor. I'm going to need to know information. I'm going to need to know my full load amps. And also what the code does. I got to remember that my motor I need to consider replacement. I may take a motor out of commission, put another motor in its place, and the motor full load amps might be a little different, right? So the code does call this out, but it's a real world scenario that I will take a motor, and maybe that motor's been in service for, God only knows how long. Let's say it's on a conveyor belt in my plant, and the dirt, the dust, the grime, the weather, I'm going to replace that motor. I'm going to buy another motor of the same horsepower, all that jazz, same type, and then I'm going to put it in. That new motor may not have the same full load amps. So what we're going to look for in the code is the provision so that I size my circuit. I want to size my conductors and other hardware that I'm not necessarily going to be able to replace all the time, based upon conservative value. I'll call it a conservative value of load. Basically I want to make sure that when I size my conductor, my infrastructure, I'm not going to base it on the actual motor that's going in, but more upon the requirements of the code that say it's in a table. I know it's in a table. It's somewhere in there that tells you what the for individual horsepower motors, what is the full load amps that you need to size things like conductors. But your overload elements, to protect the motor, I'm going to be using the actual nameplate full load amps of that motor. All right. In some cases, I'm going to have a continuous duty motor. Oh man, why does it do that? Continuous duty motor. I'll look for, this is going to be on the nameplate of the motor. I might have some other information as we go through. I'm going to have to select the right type motor for the application. I'm going to have to select the right type of a motor for the application. Could be a continuous duty, could be intermittent duty. I'll have to take into whether or not it's going to be outside in the rain versus inside, all of the different, those types of parameters. I'm trying to think of any other parameters that I might have to think about. Let me go to 430. I'm going to open 430. Robert says, Tom, hoping to see you at Western Section in Kearney. Yes, I'm going to be there. I have not reserved anything yet, but I am going to be there. Dawn says, had to change from class 20 to class 30 overloads a few times for high inertia fan loads. See, that's a very good point, Dawn. So you'll have the base, but you didn't have to change the conductors, right? So that's a critical piece of this puzzle, is that we're going to size the infrastructure so that I can put the same horsepower motors in, but each motor may need different overload protection, overload sizes, right? Because I don't want to trip the overloads. I also want to make sure that I size the infrastructure so that I don't have to change my overcurrent protective device upstream, which is, say, my circuit breaker or my motor circuit protector either, right? Okay, so, all right, so my motor's going to have a nameplate. Let's see if there is marking on motors. There we go. Here we go. Here's what's required by the code for the, this is in 430.7, has the marking requirements for a motor. I have to have the manufacturer's name, the rated volts. Oh, that's going to be really important. Rated frequency, rated full load speed, rated temperature rise, or the insulation class and rated ambient temperatures. The time, this would be like your intermittent duty. How long can you run this motor continuously, or it'll be a continuous duty type of motor. Rated horsepower, whether it's a 100 horsepower, 50, 30, whatever. Code letters for locked rotor amps. This will give you, remember the locked rotor amps. What was the locked rotor amps? We talked about that. My locked rotor amps, okay, that's my locked rotor amps. This is my full load amps. So my code letter or the locked rotor amps of it, the code letters are giving to the locked rotor amps and whatnot, or the actual locked rotor amps will be on there as well. I happen to have my design A, B, C, or D motors. This is going to be your torque speed curves, secondary volts and full load current of a wound rotor, field current and voltage for DC, excited, synchronous motors, your winding, straight shunt, stabilized shunt, all that good stuff. Carl says the locked rotor is the same. Oh, wait, hold on. Meant to say I live in New York City. The motor in my apartment AC unit inrush current causes my light fixture to flicker. Well, that's not good. Ah, I see. I live. So you started with I live. And then you said, nope, I should say I live in New York City and the motor in my apartment. I gotcha. As the inrush current. The locked rotor is the, yeah. So Carl, very good point. So I liken this to a transformer. My locked rotor amps is like your inrush current on a transformer. Very similar in nature. Although your locked rotor amps are going to persist for a longer period of time, depending upon the rotor and the stator and the load on how fast it comes up to speed. Okay. And then you have your all of your code letters for your indicating, all your locked rotor amps code letters, and that's all kilovolt amperes per horsepower with the locked rotor. All right, so that's what your marking is for the motor. So the motor is going to be marked. It's going to give you pertinent information that we're going to need, but not all of the information that we need to select the conductors, the disconnects, the overloads, the contactors, and our primary protection for overcurrents. And now, so the other thing I think about, you know how in Article 450 addresses transformer protection. 430, transformers and transformer installation, transformer protection in 450. 430 is motors and motor protection and motor installation requirements. The rest of the code still applies. Okay, don't forget about the rest of the code. So if I go to, for example, let's talk about the rest of the code. If I go to 240 for overcurrent protection, 240 should tell us there's equipment. Here we go. Look at this. It says here equipment. Remember, Article 240 is overcurrent protection. Addresses overcurrent protection of equipment and conductors. It says equipment shall be protected against overcurrent in accordance with the article in this code that covers the type of equipment specified. So if I look for motors in here, there's your motors. Motor circuits and controllers is Article 430. Okay? 450 is transformer and transformer vaults, is Article 450. Now let's talk about overcurrent protection of a conductor. Conductors, other than flexible cords, flexible cables, and fixture wires, have to be protected against overcurrent in accordance with their ampacities. So we know that. And we know that you can go to the next higher when you're protecting a conductor. We already talked about that. Where overcurrent device is rated over 800 amps, you can't go, blah, blah, blah. Small conductors, this is all about protecting the conductor. You have tap conductors. Remember, this is when you don't have overcurrent protection at the source of a tap. The conductor, the conductor that is doing the tap of the feeder is going to be smaller, and there's no protection, overcurrent protection. So we have specific rules for a tap conductor. We have fixture wires, etc. Transformer secondary conductors, remember those transformer secondary conductors in many cases are not protected at their source. So this tells you that fact that it's not protected, and that's why that's why we have the rules for transformer secondary conductors. And then over in, oh no, not over, it's still in 240 is where we have our transformer secondary conductor protection. 450 is not going to tell you how to protect the transformer secondary conductors because 450 deals with transformers. 240 deals with those conductors. All right, so then there's overcurrent protection for specific conductor applications. This says, overcurrent protection for specific conductors shall be permitted to be provided as referenced in table 240.4G, which is here. So this isn't saying that overcurrent protection for these conductors is not provided. It's telling you you're going to provide protection for those conductors. You still have to provide protection for the conductors, but it's going to be provided in these specific articles. So I should see motors right here. I got motor operated appliances, and I have motor and motor control circuit conductors. This is 430, Article 430, parts 2, 3, 4, 5, 6, and 7. All right, so this doesn't say overcurrent protection for specific conductors are not required. It said you still have the requirement to protect the conductors. It's just telling you that protection is going to be handled in each of these articles. Make sense? All right. Don Ganir says, add education power. When I teach, I call them table or code, FLA, and nameplate. Yeah, you know what? So I've heard people reference the tables in 430 as full load current, and then the nameplate data as full load amps. So FLC versus FLA. I don't care how you do it. You just have to know when to use the tables and when to not. Carl Lewis says, I've seen fast-acting fuses protect the control panel and contactor for an elevator motor in the building I supervise as a maintenance electrical, MEP, maintenance electrical professional? Oh man, I can't remember. Anyway, Redondo, full load amps ending in A for actual current, full load current. Yeah, that's exactly. Now, Redondo, is that, I don't know that that's in the code. Is that an industry thing or is that in the code? I'm going to do a search. full load current. Full load currents exceed 1%. It's only used, full load current is only used once in 24086. Full load amperes. Full load amp? Whoa. Cert. I gotta go back to 70. I got out of 70 all completely. Search. Full load amperes. There we go. Single motor. So full load amperes is used a lot. Full load current is not in the code. So I would say it's a good way to differentiate between the two. We use full load current for the table, full load amps for the actual nameplate of the motor. So, but remember, just whatever you need to do to keep it straight. Like Redondo says, that's how he remembers them. So whatever you need to do to remember them, the code uses both. Yeah. So whatever you do to remember them, then that is what I would recommend as well. So you just have to remember to use the table when you're doing some of the work around motors. Use the actual full load amps when you're doing other work around motors. All right. All right. So we talked about the motor. We talked about the nameplate information. Let's do this. Now we know the code is not a front-to-back thing. I want to pick the conductor. I don't know why, but I want to pick the conductor. That's sort of where I'm resonating right now. So I want to first pick my conductor that is feeding a motor. And I don't know, do you guys want to have a specific size motor that you want to play with? Whoa. Let me know if you have a specific horsepower or a specific motor. I don't have anything. I'm just going to try to search and let's do, here we go. Let's do this one. Let's do a 10 horsepower motor. Does that make sense? 10 horsepower? Probably should have thought about size of a motor I wanted to work on. Let's go down to the tables. I know there's a whole set of tables. 5 horsepower. There we go. Thank you. That's what I was looking for. 5 horsepower. Let's talk about a 5 horsepower motor. Oh, 150 horsepower. All right. 3-phase 208. We'll do the 5 horsepower and then we'll do the 150 horsepower. All right. So let's do, I wrote a 5 horsepower. Let's do this. 3-phase. Okay. Whoa. Copy. I'm going to scroll down. We're going to do a paste. All right. So the first, I don't know. Let me ask you guys, would you start with the conductor first? Conductor selection. All right. So we got a 3-phase. 5 horsepower. I wish I had a nameplate. Let me do a quick search. 3-phase, 5 horsepower motor nameplate. I'm just doing a quick search. I'm seeing one here. It's for sale at Granger. I got one. That's single phase. I need 3-phase. 3-phase nameplate specification guide for motors. Mike Holt, U.S. Motors, 5 horsepower. Let's try. That's a VFD. Well, what is this? Nidec, U.S. Motors, 5 horsepower, 1,800 RPMs. Let me see if there's a picture of the nameplate. Technical specs. Is that a nameplate? All right. What if we did this? Search for ball door. Okay, I'll search for ball door. Here, let's do that over here. Why am I doing this? There's a lot of good nameplates. Redondo, yeah. All right, nameplate, 5 horsepower, 208 volt, 3-phase, ball door. And let's go to images. Here, look at this. Perfect. 5 horsepower, 208, 14 amps. Oh man, look at that. I can't stand when you can't read a label. They just lost out on a sale. There we go. Here, that's horsepower 2. Boy, the one that I like, I guess we can do it. Let's do a copy image. No, I can't do that. Yeah, I can. Try to figure. Oh, I wonder if I can paste it here. Can't paste it. I can't paste it. Why can't I paste it? All right, let me just at least save this in a PowerPoint. I am going to open a PowerPoint somewhere on my computer. A PowerPoint has opened. There we go. Nameplate Enigma, recent. I know I opened up a motor program a while ago. Analysis. Motor circuit protection. There we go. New. Control V. There we go. All right, so this is going to be our nameplate. We got a 5 horsepower, amps, 14 amps at 208, 1750 RPMs. There's the frame. There's 60 hertz, 3-phase, service factor, 1.15, code J. All right, so flying by the seat of our pants the way we like it. Okay, so let's close that. We're done with that. We're going to do our conductor selection, right? So let me go, me and iPad. All right, so 430. What part in 430? We're going to go general requirements, conductor ampacity. There we go, 430.6. So 430.6 is a reference. This is our conductor ampacity and motor rating. The size of conductors supplying equipment covered by this article shall be selected from the ampacity tables in 310.15 or calculated in accordance with 310.14b. Makes sense. I can either calculate my ampacity or flexible cord. I'm not going to worry about flex cord. That's in Article 400. The required conductor ampacity and motor ratings shall be determined in accordance with 430.6a, b, c, and d. All right, so A is general motor, not the vehicle, just general motor applications. This could be like Chevy C1500 applications. Current ratings. Current ratings should be determined. Table values. So it says for general motor applications, current ratings shall be determined based upon 430.6A1 and A2. A1 is table values. Other than for motors built for low speeds, it's less than 1200 RPM. What was ours? Ours was 1750, so we're good. Or high torques, and for multi-speed motors, we don't have a multi-speed motor. Table 430.247, 248, 249, and 250 shall be used instead of the actual current rating marked on the motor nameplate. So this was, remember we were talking earlier, we want to build an infrastructure that, and yes, we're going to go to 430.22 for continuous duty. We are going to build an infrastructure for our motor circuit so that if I change the motor out and it has a different full load amps, I don't have to change my conductors out. All right, so I'm going to use the table. So if I go to 430.247, oh, and we're going to use these values to determine the ampacity of the conductor, the current rating of switches, and remember, I've got a switch disconnect, current ratings of branch circuit, short circuit, and ground fault protection. This is my short circuit and my ground fault protection, but not my overload. My overload's not going to be determined from the table. Where a motor is marked in amperes but not horsepower, what's ours marked in? Ours is marked in, it gives horsepower and it gives amps too. So it says where a motor is marked in amperes but not horsepower, so I wouldn't meet that because it's marked in both. The horsepower rating shall be assumed to be that corresponding to the value given in blah, blah, blah. Okay. And if so, I don't have to do that interpolation. I'm going to use what's in that table. All right, 430.250 for three-phase. So that's the table. Robert's telling me to go to 430.250. Let's go to 430.250. 430 full load current, three-phase, alternating currents. All right, so what was our motor? I'm going to do table 430.250, right? And our voltage, our voltage is 208. So 208 volts. Oh, I can watch this trick. If you didn't know this about NFPA link, it is a saver. Pin header. 208. I have a 5 horsepower motor, 16.7 full load amps. 16.7 full load amps. Redondo taught me this, full load current, because this is from the table, right, Redondo? I'm going to use full load current from the table. The nameplate says full load current is 14. So this has 14.0 full load amps at that voltage. Make sense? Beautiful. All right, so I'm going to go back to where I once belonged. Okay, so 430.6a tells me I'm going to use the tables for the ampacity. So I'm going to use this 16.7 amps for the ampacity of the conductor, the current ratings of the switches, the current ratings of branch circuit, short circuit, and ground fault protection. I don't have to worry about this language here. There's an exception 1 for multi-speed. Don't have to worry about that. There's an exception 2 for equipment that employs a shaded, not a shady, but a shaded pole or permanent split capacitor. Not going to worry about it. That's not my motor. That's exception 2. There's an exception 3 for listed motor operated appliances. Okay, so, and then there's nameplate. The motor nameplate shall be used to determine the valve. For motors built for lower speed than 1200, which is not me. That's when I'm going to be using the nameplate. But I'm going to be using the nameplate for separate motor overload protection. Separate motor overload protection. We're going to figure out what the heck they mean by separate probably a little later. All right, so I'm on my way. I got my torque motors. I got alternating current adjustable motors. I don't have that. All right, so but what does it tell me? It just says the size of the conductors where flexible cords is used. All right. Terminals, wiring, protection. So that's just a generic. That's just telling me where I'm going to get the data from. It's not telling me actually what my conductor size is. That's just telling me where I'm going to start from. So now I've got to come down. I got motor circuit conductors. Here we go. General requirement. This is in part 2. So I'm going to come back to this. So 430.6 is where I started. That sent me to table 430.250. Now I'm going to part 2 for what? Motor circuit conductors. And 430.22 is my single motors, my not yet married motors. So The single motor. Conductors that supply a single motor used in a continuous duty application. Now let's look at our nameplate. Let's look at this. Let's look at this. Oh, look. Look at that. Look at that. CONT, continuous duty. The rating is 40 C ambient continuous duty. So the motor is a continuous duty, and we're going to say, it says used in a continuous duty application shall have an ampacity not less than, so I'm going to say this is a continuous duty. Now remember, check out the IAEI News Live video that I did a little bit ago, this week, Tuesday. We talked about continuous current, and now I'm for motors. I don't have a continuous current for motors because they don't meet the definition of a continuous current. Go check that video out. A motor has what we call continuous duty. So that's going to be a motor that is going to operate or designed to operate continuously. So we're going to size our circuit for this continuous duty motor for this application. And the 430.22 says that the conductors that supply single motor, which I have here, have an ampacity not less than 125% of the motor full load current. Full load current, there it is, redondo. It says it right there, full load current. Doesn't say full load amps. It says full load current. And I wonder if the overload, let's go down. I know, squirrel, I'm having a squirrel moment, but I want to figure this out. The motor overload protection, where's that at? Where's the motor overload? Oh, motor control circuits, motor branch circuit, short circuit. I want overload. Motor overload protection. Provisions. Continuous duty. A separate overload device. I'm looking for, it still says full load current. The motor nameplate full load current. So they use full load current in both applications, but they'll say the nameplate full load current. So for the record, the code is using the term full load current, and they will specifically call out nameplate full load current when they want you to use the value on the nameplate. All right, so I know what we said earlier, full load amps, nameplate, full load current, book. All right, so 430.22. Conductors, so I have to take 125%. Calculator. I need a calculator. 125%. So my full load current from the table, and this is nameplate. Nameplate. The nameplate's 14. The table is 16.7. So ampacity. The ampacity, it says, must not less than. It doesn't tell you, this isn't saying that it has to be this. It can be much larger, but it can't be less than 1.25 times 16.7. 1.25 times 16.7. 1.25, enter. Where's enter? Enter. 16.7. I gotta go back. 16.7 times 25.05. So that is 25.05. That means my conductor ampacity has to be at least 25 amps. Conductors that supply a single motor used in a continuous duty application shall have an ampacity not less than 125% of the motor full load current. Now here's what it doesn't say is whether or not I have to take into consideration the termination. 110.14 applies all the time. I don't need a reference here to send me back to 110.14 to tell me I need to consider the termination, because motors are 75 degrees C application equipment. I don't have anything here that says there's, you know, I would feel better. I would feel better if it had a reference to 110.14, because what it should say conductors that supply a single motor and a continuous duty, because the 110.14 has nothing to do with ampacity. It's the continuous duty application, conductors. So the conductor has to have an ampacity, but ampacity has nothing to do with the termination, the 110.14. Don Ganir says, when you have some offline time, look at PI 3662 for the 2023. The statement pretty much says we can't use motors with voltages other than the ones in the full load current tables. Ooh, interesting. I'm going to have to take a look at that. PI 3662. That's on twice. You must have really meant that comment. All right, Dawn, I will do that. All right, so I know that a motor, does my nameplate say, I gotta close, let me close this. Control Q. All right, my nameplate, let me close that. What does my nameplate say? Boom, ba-dum, boom, ba-dum. Ryan Jackson, yes, I am doing well. Thank you for editing that PowerPoint, my friend. You are awesome. So we're talking motors, Ryan. I know probably it's everybody's favorite topic. Okay, so I don't have a temperature rating here, but I know that motor equipment, like my motor starters and things like that, are all 75 degrees C. I have to apply my 110.14, so I have it tells me my conductors that supply a single motor used in a continuous duty application shall have an ampacity not less than 125%. Now, if I'm using 90 degrees C conductors, I know my ampacity has to be not less than 125%, which is the conditions of use. That's, oh man, so this is bothering me. This is bothering me, Ryan. This is bothering me because ampacity is not a 110.14 thing. And I know my motor, I know I have 90 degrees C insulation conductor. I can't go to the 75 degrees C column for this because it says conductor ampacity. It doesn't say termination. Termination will get you to the 75 degrees C column. 110.14 reference will. So I am a little perturbed right now. I'm frustrated. So I'm going to go back to 310. I'm going to go to chapter 3. I'm going to go to 310. I'm going to open this in a new tab. Boom. Booyah. All right, 310.16. I'm going to go to 310.16. And in fact, I am not sharing my screen. Thought I was. All right, so let's go to, I'm going to pin my header. So here's my issue. It says the ampacity of the conductor cannot be less than 25 amps. I know my terminations are 75 degree. If I go by the ampacity, which is based upon the conditions of use in table 310.16, and I have 90 degrees C conductor, I would say I would be in a number 12. But if I use the 25 degree C column, I know I am in a number 10. Wow, I am perturbed. My gut's telling me if I'm reading the language verbatim, I would be using the 90° C column, because the language in 430 says conductors that supply a single motor used in a continuous duty application shall have an ampacity of not less than 125% of the motor full load current rating, or not less than specified in 430.22A through G. A is for direct currents, B is multi-speed, Y starters, part winding motors other than continuous duty, and then separate terminal enclosures, conductors for small motors. This is not a small motor. Well, 5 horsepower could be. They don't define a small motor. But that, oh man, I'm telling you what. I know what everybody does. Everybody goes to the 75° C column. But based on that language, I wouldn't go there. Because the conductor is based upon conditions of use. So for a 5 horsepower motor, based on that language, I would go to the 90° C column because I do my ampacity. And that would tell me that I am into I tried to move that provision to Article 90, but it was rejected. I'm going to try again. So Ryan, let me ask you, would you use the 90° C column here and pick a 12? Or would you use the 75° C column and pick a 10? My gut tells me it needs to be a number 10. Because I have to consider the termination, but nowhere in 430.22 does it tell me I need to consider the termination. It just says the conductor ampacity. So for this 5 horsepower motor, at 25.05 amps, based upon the conditions of use, the ampacity of the conductor is a number 12. What's Dawn saying? So, with a minimum ampacity of 20.05, can we round down? Nope. I don't believe you can. Nope. No, you can't. I have 25.05. I've got to go up. But that tells me if I'm doing ampacity, that tells me a number 12. Now, I don't have to follow the small conductor rules because I'm in a motor application, so I don't have to go back to Article 240 and look at small conductors protection. I don't like it, but it says that I can use a number 12 for a 5 horsepower motor. Dawn says, I know, Ryan, that is what the code says, but I am not going to install the next larger for 0.05 amps. Well, yeah, you got to round up, buddy. So I'm in a number 12 for a 5 horsepower motor. And a number 12 conductor is good for 30 amps. My full load amps on the nameplate is 14. 16.7 based upon the table. Reading what this stuff says, you're excluding the general requirement from your mind, which the code not having directly referenced, it assumes that you are aware of it. Are you talking about 110.14? But so here's the thing. I would agree with you, Steve. But here's my issue. Here's my issue. The language in the code says the ampacity of the conductor, which is based on, hey, Laurel, research, you should have been here, man, I'm stuck. The ampacity, the language in 430.22, the language in 430, so here's my thoughts on this, Steve. The language in 430.22 says the conductors that supply this single motor shall have an ampacity not less than 125% of the full load current, which the ampacity is the conditions of use. That's the number of conductors in a raceway and the temperature. And I'm assuming 310.16 conditions of use. That's what the 430.22 requirement says. The 110.14 is not going to make me multiply it by 125%. 110.14 is going to say, what's the full load amps? And if I say full load current is 16.7, then I need to look at the 75 degree C column for the number 12 and say, is 16.7 less than the 75 degree C column, that which will be, I'm pulling current through that termination, and that termination of a number 14 at 75 degrees C can take up to 20 amps all day, all night, 7 days a week, 365 days a year. I am not going to exceed the temperature rating on this circuit because this motor, it actually pulls 14 amps, but it could pull, I'm going to design the system for up to 16.7 amps continuously. So I'm not exceeding the 75 degree C column for a number 14 on the 16.7 full load current. So I feel good there. And that language in 430.22 says that the conductors have to have a ampacity, which I know is conditions of use, which is table 310.16. And I always go by the 90 degree C column, whatever my insulation is, not less than 125% of the motor full load current rating, which is 16.7 times 1.25, which is 25.05. So I'm good with a number 12. So I'm going with a number 12. And I feel very comfortable in that solution. If you guys and gals disagree, I need to know why. But I'm going with a number 12 for this 5 horsepower because the ampacity is 30 amps. It's greater than 25.05. I'm not going to go with a 14. I can't round down. I know Dawn would round down, but I'm not going to round down. And even if I rounded down to 25, Dawn, oh, yeah, my number 14 would still work because it can handle 20 amps at 75 degrees C. But I've got 16.7. So I'm going to stick with the 12, number 12. I round it up. I'm good to go. All right, so I have my conductor size. I have my 5 horsepower motor. What time is it? 2:48. I started at 1:30, didn't I? What's today? The 20. Today is the 5th. All right, I still got time. I'm going to go for 2 hours, I think. I still got time. All right. Is it 2:49? 2:30. I'm going to go to the top of the hour. So we picked our conductor. I mean, that's a big feat. We picked our conductor. Let's think about that conductor in relationship to the locked rotor amps and the full load amps. I'm going to have to carry the full load amps of this motor, which is, in this case, it's 14 amps based upon the nameplate continuously. I've got a number 12 that can handle 30 amps continuously. I've got a termination that can handle 25. I am golden in that case. I could make the argument that if I rounded down, is 0.05 amps going to hurt me on a number 14? Could I get away with a number 14 on a 5 horsepower motor? Maybe. My 75 degree C is 20 amps, and I've got 14 full load amps, so I'm not hurting the equipment and the termination rating. I'm also not hurting, I mean, I'm over 25 amps by 0.05. So at what point do you round up? But I'm going to round up just because I'm going by the book. Okay, so it's cheese. 430.22. So I use the parent text of 430.22. A is direct current motor rectified supplied. It's not me. Multi-speed motor is not me. Y start delta run is not me. Part winding motor is not me. Other than continuous duty, conductors for a motor used in a short time intermittent periodic or varying duty application shall have an ampacity not less than the percentage of the motor nameplate. I have a continuous duty. Personally, and I don't know what you guys think about this one, Steve and Dawn and crew, but this other than continuous duty should not be in a section called continuous duty. I mean, the title of this section is, oh no, the title is not continuous duty. The parent text says conductors that supply a single motor used in continuous duty. What I think is 430.22 should have an A, continuous duty, and give you that, and then the B would be the direct current, and then you'd have other than continuous duty. All right. The ampacity of every wire in table 3 ends with a nice round 5 or 0. There is no way that a current of less than 0.5 amps is going to cause them to fail. But the code says no. I know. But then here's the problem, Ryan. At what point do you say it's too much? No matter what, if you said it was, in our case, it was 0.05 amps. So we know what you're saying is, if you go over 0.5, that's when you go up to the next size. You go down from 0.5. From a conductor, here's another to support your argument, because I don't necessarily disagree with you. To support your argument, Ryan, if you make a public input, I'm not suggesting that you do, but if you do, I would argue that on these conductors, you can go to the next larger overcurrent protective device, which could be amps, not 0.05 amps, or not 0.5 or 0.4 or 0.1. So rounding up or rounding down for this application in the 0.5 amp range, it's not a big deal. I don't think you'll get a wire manufacturer to argue against you. Run it by Crystal and Mr. Watson, Dave Watson from Southwire. Dave Mercier, if you got Dave Mercier's email, Dave Mercier used to work for Southwire. He knows cable conductors very well. I agree with you. I don't think 0.5 amps is going to mean a hell of beans. Because then in that case, I'd put a 14 on this one. I can get away with it. But I'm going to stick with the number 12. I'm going to stick with the number 12. All right. Good dialogue. Very good dialogue. Okay, so I've got my ampacity of the conductor. I got my conductor at a number 12. And we know a number 12 can handle, so a number 12. So if I pick a 12, number 12 is 30 amps ampacity. And it is 25 amps for equipment. My equipment ampere rating is 25 amps based upon the 75 degree C column. So all of my equipment has to be rated that way. Bum, 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 bum. It wouldn't hurt if the code reiterated the termination temperature limit. Yes, that's what I think, Steve. 430 should be telling you, but here's my basic question. you wouldn't want to compare the 125% value with the equipment. You wouldn't want to go, if I did the 125%, I would be in a number 10. That would be the 75 degrees C taking 125% of the full load amps, full load current that's based out in the table. And it depends on why it is we do that. If we're doing the 125% because my locked rotor amps and my, that transition from locked rotor to full load amps might have a heating impact, like if it's on a conveyor belt, but the application doesn't come into play here. They're just simply talking continuous duty, like a continuous load. I'm not I'm not going to worry about that. So, but I agree with you. What they should do is say that you need to protect your equipment at that 75 degree C column. So your overloads, my overload should not be more than 25 amps for this application. For a number 12, my overload should not be more than 25 amps because I would not want more than 25 amps flowing through my termination for a continuous duty, for any duty. Because we don't test our equipment with current flowing through the terminations at a value greater than what's in table 310.16 in the 75 degree C column. So somewhere in 430, and we'll look at the overload, I would go to the overload protection. The overload protection is where I need my 110.14 reference. It would not, oh man, this is like beautiful. It would not make sense that I would put a 110.14 reference into this section of the code because this section of the code is just dealing with the conductor selection. And it's telling me what my minimum size is. It doesn't tell me that I'm going to end up using a number 12. It says I can't go less than a number 12. When I go to my overload protection, I need to protect this number 12. I can't have an overload protection at greater than a 25 amps, which is in the 75 degree C column. I would expect that in 430, in the overload, when I'm selecting my overload, that it should have a reference to 110.14 for the termination. That's where the 110.14 reference should be. And it may require that I increase that number 12 to a larger conductor, because all that this section is telling me, the only thing that 430.22 is telling me is the ampacity must not be less than 125% of the full load current rating. It doesn't tell me that's what it's got to be. I could have to go larger for a few different reasons. Voltage drop might be one of them. Voltage drop could be one that it's not a conditions of use. It's not driven by conditions of use. It's the length of that conductor that's driving the voltage down. Or it could be not the length of that conductor. It could be my starting voltage is low enough that my length of conductor is driving my voltage at my motor terminals too low. But I mean, you got to be, these motors are 460 volts. So I mean, if I'm at a 480 volt system, that 460 volts already accounts for the voltage drop. So I shouldn't have a voltage drop issue. But what this language says is that the ampacity can't be less than 125% of the motor full load current. This is not telling you that that's the size of the conductor you can use. We haven't determined that yet. All we've determined in this journey is that this is the minimum size. That's the only thing we've determined. We haven't determined the actual size. Right now in our minds, we're using a number 12. We may not end up there. So that's, I'm glad we had that discussion. So 430.22. Now let's talk about the overload. That's the next step. And what I'm going to do is I'm going to introduce the topic of the overload protection. I'm glad. So I'm going to wrap a bow around the conductor. And all we've done in our session today is we've identified the minimum size of the conductor necessary for this 5 horsepower motor, not the actual conductor that's going to be used, just the minimum. We're going to go to the overload protection. That's going to give us the other part of our story to ensure our conductor is protected and the motor is protected, because we don't get forgiveness in the conductor protection. We still have to protect the conductor. It's just 430 is going to get us there. All right, so 430, and where we're going to go for the overload protection is in, I think, part 3. Is it part 3? I'm still in chapter 3. I'm going to go to 430. Part 2 is your motor circuit conductors. And now part 3 is your motor and branch circuit overload protection. And it says part 3 specifies overload devices intended to protect motors, motor control apparatus, and motor branch circuit conductors. So we know that this overload device is going to have to provide protection for our conductor because it says it. And we know that's going to be at the ampacity, right? So, and we know from 240 and to our discussion earlier, that I can go to the next larger if I'm using like a circuit breaker where my overload protection is a part of the circuit breaker. I could go to the next larger overcurrent protective device when it doesn't equal a branch circuit overcurrent device standard ampere rating based on 240, based on Article 240, 240.6, I think it is. So for the conductor protection, I think it's pretty simple. And in this case, a number 12, I can put a 30 amp overload on it, and I don't think I'm going to be using a 30 amp overload. I don't know on this motor, but we're going to determine that. Part 3 is specific. Okay, so we know what part 3 does. 430.32 is going to be our continuous duty motors, and motor with more than 1 horsepower, because we got 5, so we know we're in 430.32A. Each motor used in a continuous duty application and rated more than 1 horsepower has to be protected against an overload by one of the means. So I'm going to go back to my drawing, and I'm going to say this is a separate overload. So A1 is a separate overload device. This would be an A1, 430.32, 430.32A1. That is a separate overload device. A2 is a thermally protected or electronically protected motor. I'm not going. This would be a 430.32. A2 would be a thermally protected or electronically protected motor. And then A3 is integral with the motor. And then A4 is larger than 1,500 horsepower. That's not going to apply to us. So I'm going to be doing A1, separate overload device. We're going to go down this road first. Then we're going to go to maybe a circuit breaker or a fuse that does the whole shebang. I'm just going to consider a contactor overload separate. All right, separate overload device, a separate overload device that is responsive to motor current. This device shall be selected to trip or be rated at not more than, what's our service factor? What is our service factor? our service factor is, what is our service factor? Class F. Service factor 1.15. Okay. Motors that are marked service factor 1.15 or greater is 125%. Motors with a marked temperature rise, 40 degrees C or less, is 125%. Good. All other motors are motors. All other motors. Some motors, redundo. Some motors have internal overload protection. Yes, that's right. We're not going to do that one. That's going to be different. We're going to do A1 right now. We'll get to the internal ones. So I'm at the separate overload has to be set at 125% of the motor nameplate. And we said the motor nameplate was 14 amps. So let's talk overload. Hold on, let's do this. I am going to select this. And I'm going to do copy. I'm going to bring this down here and do paste. And I'm going to get rid of this. And I'm going to get rid of this. All right. So overload. Whoa. Overload. Over hill, over dale. 125%. It says the device shall trip or be rated at not more than. So I could be less than. So 430.32A1 overload not greater than, more than 125% times FLA. And I'm using FLA because that's the motor now. 1.25 times, and the motor full load amps was 14. 14.0 equals 14, 144, enter, 1.25 times 17.5. 17.5. So I can't be greater. So I can't go to the next larger because it says the device shall be selected to trip or shall be rated at not more than the following percent of the motor nameplate. And you can modify that based on 430.32 Charlie. What is Charlie? 430.32 Charlie. Where the sensing element or setting or sizing of the overload device selected is not sufficient to start the motor, a higher size sensing element or incrementing settings or sizing shall be permitted to be used, provided the trip current of the overload device does not exceed the following percentage. So I can go to maximum 140% per C in 430.32. So 1.4 times 14 is equal to what? 1.4. Enter. 1.4 times 19.6. 19.6. So my overload can be 17.5 and up to 19.6. Now what I want to do is I want to make sure that my minimum conductor size, remember what my minimum conductor size? It was a number 12. To protect the equipment based on 110.14, I cannot exceed the 75 degree C column for the ampere, the value of current for a number 12 conductor landed on 75 degree C equipment. And that value is 25 amps. So both this number and this number are greater than 25 amps, which is the 75 degree C column for a number 14 conductor. So that tells me I am protecting the conductor from overload. I'm giving it protection, and I am protecting the equipment at its 75 degree C temperature rating for a number 14 conductor. I love it when a plan comes together. You see the fundamental that we talked about in 210, we talked about in 110.14, we talked about in 215 and in 230. We said that the conductor has an ampacity. It is not related to the equipment. I can carry what is in 310.16 and I adjust the values in 310.16 based upon the conditions of use, which is ambient temperature and the number of conductors in a raceway. I could do that modification. I can do that analysis for the ampacity of the conductor. I take that and I put it over there. I put it up here and put it in the back of my head. Then I have to worry about my equipment. If my equipment is rated for 75 degrees C or 60 degrees C, for that size conductor landed on that termination, I can't pull more than whatever is in the appropriate column of 310.16 through that termination. All of that is done in 430. Remember, 240 gave up purview. In 240 it said, look, the conductor is considered protected, and the equipment, remember early on it says equipment is considered protected based upon what's in 430. The conductor is considered protected based upon what's in 430. So we have to make sure that the rules of the language in 430 protect the conductor and the equipment. And so far, even for increasing the size of the motor overload, my termination and my equipment is protected from overload because I'm less than the 75 degree C column. And my conductor is protected because I'm less than the ampacity of the conductor. Because remember, I have a 19.6 overload, 19.6, and my conductor ampacity for a number 12 is 30 amps. And to Dawn's point, and the discussion that we just had earlier with Ryan Jackson, I'll bet you I can get away with a number 14. Because a number 14 has an ampacity of 25 amps, and the 75 degree C column for a number 14 is 20 amps. 19.6 is less than 20 amps. I'm feeling like I could get away with a number 14. I'm just saying. Carl, can you use a VFD to reduce the motor starting inrush current? Carl Lewis, yes you can. So the nice thing about, and we're going to cover a VFD in the next one, because remember, we're going to have a whole series here on motors. So what got us down this journey is sizing the conductor and the overcurrent protected device. We're talking ampacity. We are exploring, and this is a master class in ampacity. When we get done with this, if you watched from soup to nuts, you will know more about ampacity than you care to know. And if you violate the code or you violate equipment applications, it's your own fault. Because I've made mistakes. You've helped me correct them throughout this entire journey. So you got to watch the whole series. And Carl, to your point, we're going to throw a VFD in here and we're going to look at VFD requirements. But yes, the variable frequency drive takes care of ramping up the motor and all that jazz. The VFD isolates you from the activities in that motor and the requirements from inrush currents and all that jazz, because it will ramp that motor up, it will ramp it down, it'll start it, it'll stop it. It does everything for you, and the conductors and overcurrent protection on the line side of that VFD, so much, you can breathe a lot easier because the conductors and all that jazz, Even the fault contribution, as long as you don't have a bypass on it, you're not going to have fault contribution back into the system. VFDs have a lot of value, a lot of value. Now, they come with a cost, price-wise. And they'll give you some third harmonics in some cases, depending upon the pulse of the drives, all that jazz. You may have to upsize the neutrals or whatnot. I don't know. We'll probably get into that because this is an Ampacity discussion, whether it's the phase conductors or the neutral conductors. We're going to talk about it. So, but very good question, Carl. And hopefully this session gave you the bug to want to sit through more. So, Ryan, yes, I am going to see you in a couple weeks. Looking forward to it. Ryan Jackson is going to be doing a presentation at the Western section, in addition to help us conveying Chapter 3 code changes. And I think there's another, isn't there two? I think there's two code-making panels that he sits on. I'm almost positive you're doing another one, and I know you're doing a presentation. So we're gonna get an overdose of Ryan Jackson and Laurel. I hope we are going to see you there. Are we going to see you at the Western section, Laurel? We're going to see Robert from Omaha. We're going to see him there. We're going to see a bunch of other people. So hopefully you guys and gals can show up to the Western section meeting. Looking forward to talking code with all of you, and maybe argue over a beverage or two. So, and a good dinner or lunch or whatever. All right. Thanks everybody for tuning in. I appreciate you, and I appreciate your patience as I walk through and learn about ampacity and overcurrent protection, and now journey the motors and motor circuits. Carl Lewis, thanks for joining in. Steve Spiker, Redondo, thank you, and my buddy Ryan Jackson, and everybody else. So Felix and everybody else. Thanks for joining in. Thanks for watching. And Steve's comment. Hold on. Informational note number 2 of 430.21. 430.21. 430.21, general. Informational note number 2. There it is. Thank you, Steve. Thank you, Felix. There it is. It's right there in big, not bold letters and not big letters, but Steve's comments. 430.21. C 110.14c and 430.9b for equipment device terminal requirements. Here's the other nice thing about NFPA link. What is 19b? Motor controllers and terminals of control circuit devices shall be connected with copper conductors unless identified for use with different. All right, so here's my issue, Steve. ISO recording and it was stopped. All right, well, it stopped recording locally. It says and passive conductors are capable of carrying motor current without overheating. And then part 2 shall not apply to motor circuits rated over 1,000 volts. All right. So in any case, we do have a reference to 110.14, and that is a good thing. Thank you. Thanks, everybody. Thanks, Felix. Thank you, and Carl, for dialing in. And I'm doing what I can with what I got, which ain't much. All right, everybody. Take care, stay safe, and we will see you next time for a continuation of Ampacity with regard to motors. Stay safe.